Hi, welcome to the ARC Future Timber Hub Research Showcase. Today is the Griffith University Showcase, and it's number 3 of 5 in the series. As you can see, we've had the University of Queensland Structures and Architecture Showcase, the Queensland Department of Agriculture and Fisheries Showcase, and tomorrow we've got the University of Canterbury Showcase and the University of Queensland Fire Showcase. Just to introduce myself, I'm Kelly Reichmiller. I'm the ARC Future Timber Hub Manager. And next to me, we've got Lisa, who is the chair of today's session. Lisa is a lecturer at the University of Queensland School of Civil Engineering, and she specialises in timber structures. So a little bit about the ARC Future Timber Hub. It's an Australian Research Council industrial transformation research hub to transform future tall timber buildings. The aim of the hub is to transform the Australian timber construction industry by generating the skills, knowledge and resources that will overcome current technological and social barriers that limit the application of timber to tall structures. By bringing together experts from industry, government and academia. So this is a list of our partners. So we've got the Queensland Government, the Department of Agriculture and Fisheries, UQ, the Queensland Fire and Emergency Services, Hine Timber, Arup, Lendlease, Scion, the University of Canterbury, Griffith University and the University of British Columbia. We've also got other partners which are part of the sub-projects under the hub. We formed a unique partnership that spans the entire timber supply chain from primary producer to construction regulator. Our interdisciplinary team includes product manufacturers and wood scientists, architects and structural engineers, fire safety engineers and construction managers. So I'll now hand over to Lisa, who will introduce the projects.
Thank you, Kelly. So the next project is, as I mentioned, the third one of the DAF projects. And the title is the optimization of wood-based mass panels for Australian building systems. And the presentation will cover this 3 project progress towards investigating 3 key areas. The rolling shear performance of COT using Australian species, the development of a mechanically laminated panel, specifically NLT, so that's nail laminated timber from Australian feedstock, and the development of a veneer-based panel with high connection performance for use as core walls. And the speaker for that presentation is Tony Dakin, and he's a principal research scientist at DAF Salisbury Research Facility. He specializes in timber products and performance. And in total, Tony has over 15 years timber industry and research experience. Prior to joining DAF, he worked for Hine Timber as a product development engineer, focusing on improving products and processes related to structural and preservative treated timber products. Tony's leading the project that he's about to present, but also contributes to other DAF-led future Timber Hub projects. And with that, over to you, Tony.
Okay, so thanks for the introduction, Lisa. And as you mentioned today, I'm presenting on a DAF project, and that project is the optimization of wood-based mass panels for Australian building systems. First, some acknowledgements for assistance on the project. Of course, there are numerous contributors and collaborators to a project of this magnitude. A number of colleagues at DAF need a mention. Bill Leggett, our team leader, Rod McGavin, project leader, Shandon Kumar and Adam Faircloth, key researchers, along with all the technicians and research assistants. Along with those guys, John Shanks from Timber Ed Services, who has contributed enormously to the content and progress of this project. Our academic friends at UQ Griffith and the University of Canterbury, among others, and also the companies who have provided materials for experimental work that you can see listed there on the screen. So to give some context initially to today's presentation, a sentence that warrants its own slide, and that's the overarching aim for the project, which is develop new or refine existing wood-based mass panel products specifically for use in Australia. So starting off, like all sizable research projects, we started with a literature review. In the case of this project, it was much more than just a review of relevant research that was documented in journals, etc. It included an extensive look at both current and potential engineered wood product markets and supply chains, as well as consideration of current and future products, feedstocks and manufacturer processes. And of course, the purpose of the review was to identify research needs and shape the experimental phase of the project. So following on from the literature review, a prioritisation process was undertaken to identify the key topics for further research. This involved extensive stakeholder engagement, and final agreement on the topics came about via a stakeholder engagement workshop that involved about 20 participants. 4 key areas were selected for further research. The first being refinement of Australian produced CLT, specifically with regards to investigating the rolling shear performance of feedstock and its effect on panel performance. Secondly, the development of a nail laminated product suitable to achieve typical residential and commercial floor spans, and an increased understanding of the parameters that affect the design to go along with that. Thirdly, the development of veneer-based mass panel with optimised connection performance for use in the core walls of buildings. And finally, in collaboration with Dylan Fernando, who's formerly UQ and now RMIT, was the development of a glue line performance models and the impact of production parameters on bond performance. So my presentation today will focus on those first 3 topics. Okay, firstly, I'll present the work related to rolling shear performance of CLT. Why do we need to investigate the rolling shear performance of CLT? Well, firstly, CLT is at the forefront of the mass timber revolution. To maintain the momentum in this growing market and for other mass timber products, we need to have a sound understanding of the properties and performance of CLT to ensure that a quality product is provided to maintain consumer confidence. Further to this, no extensive research or standardisation of test methodologies and product design models has been conducted specifically in the Australian production context. Suppliers are currently adopting rolling shear properties that appear as though they might be overly conservative. And why does this matter? Well, because the rolling shear performance of the centre layers contribute to the bending performance of the overall CLT panel, particularly in the serviceability or stiffness aspect, which is typically the critical factor in long span floor panel design. So with better understanding and better rolling shear properties adopted, this could lead to larger spans or even shallower panels if producers were prepared to change their laminate sizes. And both of these would potentially result in reduced building costs. So several factors were assessed as part of this work. These variables include different species such as southern radiata and hoop pine, different grades or in particular stiffnesses of feedstock, varying aspect ratios of the centre laminates, or essentially different cross sections of boards used in the perpendicular layers, a low, medium and high moisture content level of different feedstock were considered, and perhaps most interestingly, the performance of knotty as opposed to clear boards. Normally defects in timber are associated with lower performance, but in the case of rolling shear, it's hypothesised that the knots may actually reinforce the board in fact, so we decided we'd check that out. The results, so what have we found? Well, in-depth analysis of test data is continuing, but I have got a few clear findings I can present today. So firstly, depending on the specifics of the test method that we employed, rolling shear test properties were regularly 3 or more times greater than the values currently adopted by industry. Extrapolating this out, this potentially provides somewhere in the order of an 8% increase in CLT bending stiffness properties and then hence performance in floors. Rolling shear properties were relatively consistent for each species and independent of feedstock grade. What this allows is the optimization of panels by directing higher grade material to the longitudinal layers where bending properties are more critical, given that most grades of material have similar rolling shear properties for the core layers. Rolling shear performance decreases with increased moisture content feedstock, feedstock moisture content. During testing, the average rolling shear modulus actually dropped by somewhere in the order of 30% when the moisture content of the boards increased from 12 to 16%. As such, this sort of identifies that as that moisture content control is clearly something that needs to be considered by manufacturers. And finally, knotty boards did in fact significantly outperform clear boards in rolling shear. The magnitude of this improvement changes between the species. And again, this provides the opportunity to optimize panels by strategically placing different feedstock qualities during the manufacture process. Now moving on to the NLT work. Kicking off, why did we investigate NLT? Firstly, it's thought to provide an agile, low-tech and low capital opportunity for existing manufacturers with supply chains in place, like the truss and frame guys, to produce a wood-based mass panel product. To illustrate that point, the photo on the right basically constitutes all the equipment you need to commence NLT fabrication. Further to this, NLT provides the opportunity to incorporate multiple performance criteria into the basic panel. So these criteria may include the structural performance, acoustics, visually expressive ceiling soffit, and perhaps even a floor wearing surface. And in addition, the feedstock options potentially include currently undervalued products such as short length and low grade material. So the primary aim of the NLT work was to understand and quantify how various fabrication factors affect the performance of the overall panel. This would, of course, then allow us to design and develop prototype NLT panels suitable for different floor spans. So as I mentioned previously, the serviceability criteria typically governs the design of long span panelised floors. And this includes both vibrational and static bending performance. As such, we tested for both of these cases, and I've indicated those test methods over the coming couple of slides. Firstly, this was the vibration test setup, simply using an impact hammer and accelerometer to measure the vibrations imparted and how they dissipated. And then on this slide, the static performance was done by your basic 4-point static bending test arrangement. So the same approach to testing was taken for all sample types and parameters we are researching. Individual boards were tested vibrationally and statically, then clamped together in sets of 5 and tested again. And then finally, the 5 were nailed together with a given pattern and tested once more. This allowed the quantification of the effect of both feedstock and panel assembly factors. And to be more representative of the kind of spans this product is designed for in application, a long span to depth ratio of around 30D was adopted in all cases. So a large variety of, oops, I've gone too far. Okay, a large variety of factors were considered and quantified through testing. In the interest of time today, I won't discuss them all in detail here, but I have provided some examples over the coming couple of slides. So factors that were assessed included butt joints for joining together short material into long length laminates, also the surface finish of the boards used as laminates. And on this slide, the arrangement of laminates, and also details of the nailing patterns, spacing, etc. that was used. Okay, some results. So as was the case for the CLT, in-depth data analysis is still ongoing. There is a number of positive outcomes, however, to share. overall, all of the factors of interest were able to be successfully quantified, and I've got a few examples of those here. Multiple butt jointing options were developed that impacted performance by less than 10% when compared to solid boards. So this certainly makes the use of short length feedstock more palatable and viable. No difference in the static performance of NLT panels was observed based on the surface finish of the laminates. However, a 50% increase in the damping ratio was achieved by rougher header versus smooth dress boards. We're able to obtain a 30% increase in NLT panel flexural rigidity by staggering the laminates rather than having a simple parallel alignment. That's obviously specific to the arrangement that we tested, the configuration that we tested, but a trend that would hold. And what this potentially allows is a target performance to be achieved with lower grade feedstock or increased performance of a panel without additional material expense. The impact of nailing parameters on NLT performance was confirmed. And overall, the quantification of a wide range of NLT design parameters puts us in the perfect position to design and prototype fit for purpose NLT products. And last but not least, the veneer-based mass panel product for use as core walls. Again, why are we considering veneer-based panels? So the project did publish an editorial article in the Bioresources Journal discussing that in detail. I've reproduced some of the key points here on this slide. As we know, CLT is a great product, but unfortunately its connection capacity somewhat limits its viability for use in the core or stability walls of large buildings. And that's resulting in concrete still being adopted by building designers. Veneer-based products potentially have significantly improved connection performance versus CLT. For example, the joint strength group of commercially available LVL is a JD3, whereas the pine boards used in CLT manufacture are typically only somewhere around JD5. So this roughly indicates somewhere in the order of double the joint capacity for the LVL versus the pine. And also there is a underlying resource utilization benefit in using veneers as opposed to sawn boards. As the log sizes and qualities that we've got available continue to reduce, the peeling of logs rather than sawing provides an opportunity to maximise not just the overall fibre, but more importantly, the quality fibre recovery. And this is demonstrated in the diagram there on the bottom right, with blue representing higher quality wood and red the lower stuff at the core of the log. Okay, so the aim, as mentioned, of this body of work was to develop a veneer-based mass panel product suitable for use in the core walls of large timber buildings. So in order to do this, we first need to gain an understanding of the underlying material properties that affect connection design. And we were particularly interested in those required by the European yield model for connection design. And subsequently, we tested some different options for density, bearing strength, embedment strength, and screw withdrawal strength. And on top of analysing the underlying material properties, we also tested some large-scale prototype screw connection to assess the performance of joints under simulated core wall applications. I've provided some more details of this testing over the coming couple of slides, but again, in the interest of time, I'll push through pretty quick. Okay, so firstly, the underlying connection properties. Shown on this slide is details of testing undertaken on the embedment strength of the veneer-based mass panel designs we came up with. As you can see, various tests were conducted with regards to fastener and veneer orientation. Similar to the embedment strength, bearing strength testing was conducted in various orientations. As shown in the sketches there, samples were orientated so that bearing loads were applied longitudinally and to the face and edge of panels. And again, screw withdrawal strength was conducted in various orientations appropriate to core wall applications. Screws were tested from the face and edge of panels, both for thread withdrawal and head pull through. And as I mentioned, testing was also conducted on large scale specimens to assess different screw patterns under simulated in-service loading conditions. 3 different screw configurations were tested, as shown on the left of the screen. The first there contains a pair of perpendicular screws only. The second uses diagonally opposed angled screws. And finally, the third one is a combination of both. So the screws that we selected and the configurations that we used were chosen to allow direct comparison to results obtained from the same testing on CLT that was conducted by the guys over at the University of Canterbury. So the prototype joints were tested under monatomic loading conditions here at Salisbury, and the cyclic testing by Benoit down at Griffith. So the results for veneer-based mass panels, as is the case for the other topics, the in-depth data analysis is continuing, but some very important results have been quantified thus far. Okay, so firstly, veneer-based mass panels made by simply laminating commercially available LVL together displayed very similar joint strength capacities to CLT, tested with the same fastener groups over at Canterbury. Interestingly though, the slip modulus or joint stiffness was at least 30% greater for veneer-based mass panels in these tests. We had a look at the including crossbands for panel stability, and these had varying impacts depending upon the connection property and the fastener orientation being assessed. So overall, this is all looking very positive, and we're currently looking at these results in terms of core wall performance and what the optimum panel design might be. Okay, so wrapping up, where to next? Well, there's still a lot to do on the project, but in terms of outputs, all testing is complete. The data analysis is currently being finalised. The final technical reports for the project are currently being drafted. And on top of this, we're also planning to turn these reports into somewhere in the order of 5 manuscripts of publication across the 3 topics I've discussed today. And that's a summary of the work to date on the optimisation of wood-based mass panel project. So I guess I throw back to you, Lisa, to for any questions and the like.
So today was the 3rd of the 5 in the series. So tomorrow we've got the showcase, the University of Canterbury showcase. And then on Friday, we've got the University of Queensland Fire Showcase. So you're still able to register if you haven't already. Again, the webinars will be recorded, so you'll receive an email once the recording is available to review. So thank you.
Thank you all for attending, and thanks our speakers of today. See you tomorrow, hopefully.